Okay. So, and I didn't check if it's looking at me. Let's make sure it's looking at me. You might be on camera.
Oh, sure.
It's okay. This is for the online students, but also when it's online, then you can all refer back to it if you need to.
Okay.
So far this semester, actually, let me make a quick logistical announcement first. Next week, I'm leaving on Wednesday, and for a conference we've been invited to. So leaving Wednesday and returning Wednesday next week. So I can either assign something for you to work on in lieu of that class that we would miss next week, or we could try to schedule a makeup session maybe on the Friday of that week before midterms.
Okay.
You don't have to decide right this second. I guess it depends on Mona as well, but just for you to be aware. So far this semester we have this is intro to calculus, and we've looked at limits, which are very closely connected to the fundamental. The heart of calculus is derivatives and differentiation. But the other parts, there's the complement of differentiation, which is integration, which is in a way the reverse operation. We haven't looked at it, we will look at it after the midterm.
Okay.
But those are the two main parts, and limits are what allow us to do these two things, differentiate and integrate. And we've done limits, and I think you're okay with that. I know we didn't cover the laws of limits in class, but they're pretty straightforward, and you can read on them by yourself. And if you have questions, then we could discuss. So more recently, last week, we looked at derivatives and the rules of differentiation, as you remember. And I can bring up. Here we had these proofs of differentiation rules, so the sum and difference rules, and we convinced ourselves that it is in fact true that that the derivative of the sum of two functions or the difference of two functions is the sum or difference of the derivatives of the two functions through this derivation. And for that we needed to use the sum and difference laws for limits in order to prove that the same is true for derivatives. So that was pretty straightforward. And then we proved the product rule as well, which was a little bit more interesting than the sum and difference, where the derivative of a product is not simply the product of the derivatives, but it's this slightly more interesting f times the derivative of g plus the derivative of f times g, if you're taking the derivative of f times g. And then we proved how that is true. Again, we had to use some laws of limits, that in this case, that the limit of a product, we have this thing times this thing is equal to the product of the limits. So we can say the limit of this part times the limit of this part.
Yeah.
And with that, and then the same for the second term over here, and then we just carried out the limits and we obtained the result. And then we did an example to show that using actual functions, this is in fact true, and we can show that. And then we reviewed the power rule, which I think you had already covered for yourself, which is one of the most used sort of rules of derivatives, that any a variable to a power, when you take its derivative with respect to that variable, you bring down the power as a coefficient in front, as a constant, and then you subtract 1 from the power. And the special case where there is no x, in the sense x is x to the 0, you don't subtract 1 from the 0, but rather the derivative becomes 0. So this is a special case of, this is the constant rule. What else did we do? Then we introduced the quotient rule, which gets a bit more complicated and can be proven. It's easier to prove if we use the chain rule, but then the chain rule we hadn't yet introduced. So I did that very quickly here, and I can understand if that lost you. That one is a bit more conceptually what's going on here.
Yeah.
So let's start off from there, but let's maybe, the midterms will be in 2 weeks, and it will be about limits and derivatives and applying the rules of derivatives. So I said last time, it won't be prove these rules, but do you know the rules and can you use them to solve problems? That's what it will be about. So I think for today, we can go over the rules more. There's also, there are some other sort of the derivatives of trigonometric functions, the derivatives of exponential and logarithmic functions. That would complete, if we cover those, that would complete sort of most of what one needs to understand and use, be able to use derivatives.
Okay.
So if I say, let me start a fresh file here and say, actually, I think I prefer to put it down like that. Well, you can see it up there too, I suppose. So we have covered power rule, or sorry, what am I trying to say? Well, we have power and quotient rules. We've done the sum and difference rules, of course, those are pretty easy. And then we just introduced at the very end the chain rule, but we can review that.
Yeah. Wasn't understandable.
And then, sorry, not the power rule. I realize what I meant here. This is the product rule. And then this is sort of one set of rules. Another set of rules is, actually, we'll start with there's the constant power. Then there's trigonometric, exponential, and logarithmic. Trigonometric. So this is all related to differentiation. So these ones over here, this set, I don't want to put that in there, but these are to do with so rules about functions. How do you call it? These are how to sorry, I'm gonna delete it. This is how to combine functions or deal with combinations of functions. Right?
Okay.
By the way, did you get the file that I sent for last week's lecture?
Yeah, I did.
Could you read it? And
But then the audio wasn't available.
it wasn't?
Yeah.
Maybe I have to change the format?
This one. Yeah. It was zipped. Proof of demonstration the next. But then,
It was zipped?
yeah.
Oh.
So I managed to unzip it. But the
Oh, you could
audio.
ask me. I thought it was just there. Okay, we can look at that. Okay. So this one's on the left are about how we differentiate combinations of functions, right? So we could have f plus g, f minus g, f times g, f divided by g, and finally we have f of g. So g, remember, is a function. So in a sense, there's a g of x, right? And the question in all of these cases is, what is the derivative with respect to x of whichever one of these things? So that's what these ones on the left are about. So they don't tell you, if I actually give you now a function, right? If I say f is, so in this case, f is a constant a. Here, f is the power of x. Trigonometric, f is, let's say, sine. This is getting too tight here. Let's undo that. Let's say, maybe I should move them down, but I wanted to keep them on the same screen. Oh, I know. I can at least move them over a bit. There we go. So here, f is sine of x. Exponential would be, well, we won't make it e yet, but we'll say a to the x. And logarithmic is f is the log of x. And so, in a sense, these ones on the right are about, now, if I give you an actual function, what is actually the derivative? You need these ones on the right.
Okay.
And the ones on the left, the rules, will help you as you see functions. You learn to say, ooh, I think I need one of these rules from the left, right? So if I write a function like f is x to the 3 minus sine of x. Okay, so you have part of this is a power, and part of it is a trigonometric function. And so you might say, what is, well, not write it that way. What is f prime? Well, it would be the prime of x cubed minus the prime of sine of x. Oops, x cubed. That's not what I wanted. I wanted primed. You understand what it means when I write this in brackets prime? Yeah. So the other way to write it, just for everybody's benefit, would be like this. Minus d by dx of sine x. That would be the same thing. And just for consistency, we would write it like this. Both of these are the same thing.
Okay.
So, in a sense, we've used the difference rule to say, well, I have this bit on the left, and this bit on the left, and another bit on the right. And so I can take the derivative of the whole function of f is the derivative of, is the difference of the derivatives of each of the parts. And then I would go up here and say, okay, I know what the rule is for differentiating a power. I know the rule for differentiating a trigonometric function. We don't actually know it yet, but there is one. And so then I can do each of these, and then I put it together, and I get my answer.
Okay.
And that's essentially how you take derivatives. You're given a function, you look at it. It takes some practice to be able to look at a function and think, ooh, I think what I need to do, the approach is to first do this, and then this, and then this. So it's in one way, it's a bit like a puzzle. They're not hard puzzles. Well, some of them become hard puzzles, but we're not going to go to the very hard puzzles.
Okay.
But that's essentially the idea of working with derivatives. So the strategy is you look at a function, and the more you do them, the more familiar you become with using these.
Okay.
So like by now, I just look at it and I just do it. I don't even think, oh, I'm using the quotient rule, I'm using a trigonometric thing. I just know what it is and I do it. But that comes with practice.
Okay.
So I guess for today, we have not yet covered these guys, and we really
No.
glossed over the chain rule. But you're okay with the other ones.
Yeah,
So
yeah,
if
yeah,
I'll
power,
just put them in blue.
product, and then-
Product, quotient, sum. You said the quotient was a bit.
Actually, since the quotient was the one introducing the chain rule, I think it might be good if you start from the quotient rule. But then the product, the sum and difference, the cost and the power, actually know them.
Those are okay.
Yeah, those are okay.
Is the okay? We'll start with the quotient rule. I think it's in a sense. I'm sure you understand the quotient rule.
Yeah.
Proving it is the trickier part, and I used the chain rule to make it easier to prove the quotient rule. But you don't actually use the chain rule when using the quotient rule.
Okay.
I only used it for the proof of the quotient rule.
Oh, right. So then
So
we said the formula for the quotient rule.
do you remember?
I think it
So
was
let's start.
prime of x multiplied by g of x.
So quotient rule was we have f divided by g, d by dx, which is f over g prime, and it's, I always have to remember which one is the one that has the minus sign.
This one has the minus sign.
Is that the way around?
Yeah, the quotient has the minus sign.
I mean, I know, but which one is it f prime g, or does it start with f g prime? That's the part that I never quite remember.
I thought we're just using the same same product rule, right, in the top. So I actually understood it with f prime multiplied by g of x minus g prime multiplied by f of x over g x squared.
So you're saying f prime times g minus g prime times f over g squared. And my question is it this, or is it f g prime minus f prime g over g squared? And these two are not the same. So is it this one, or is it this one?
I think the first one.
So let's check my notes. Nope, not this one. Proof of differentiation rule. So what had we said? F prime g minus g prime f. F prime g minus g prime f. You are correct. Excellent. So, very good. So this is the quotient rule. Now, using it, how would you feel about using it? Using this rule?
I haven't yet used it in anything.
You haven't used it yet in anything?
Yeah, no.
Shall we try using it? If I give you a function, or a quotient of functions, actually. So we'll take some simple ones. Let's go x cubed minus x over x squared plus 3. And I want the derivative of this. Do you want to do it on here, or do you want to do it in your... I'll copy what you're doing so that everybody sees.
Okay. How?
Oh, by the way, I wanted to mention something that I was taught in school that has been very useful in my life. It was actually in physics class, but he would say if you're given a problem, especially word problems, where it says somebody goes to the store and they have to travel this far and do this and that and find how long it takes to blah, 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 blah. And so he would say, first thing is write everything that you are given, that you know.
Yeah.
And then what is it that you're being asked to find? So before you even start trying to solve anything, you would first start with, what do I know? What am I given? And sometimes you're given more information than you need. So you write down everything you're given.
Yeah.
And we would write, for example, the initial distance was 0 and the final distance was 3 kilometers and the speed was 3 kilometers an hour, and we're being asked for the time. The start time was 0, and we're being asked for how long it took to get there. So I would write down all the things that I know from the story, and then I would say, okay, if I look at all of these, what laws or formulas or the equations would help me to find the thing that I'm looking for? And sometimes it would even have 2 things you're looking for, maybe.
Yeah.
Then I think, okay, which one will I find first? And then I can find the other one, and so on. Now, physics is not pure math, but it uses math. But this approach of, and every problem, every time we gave him a homework, we had to show this. If we didn't do this, he would take off marks. But it was very good practice to first be clear, what do I know? What am I given? And what am I being asked to find? And only after I've written this, then I start writing down, okay, well, I know that, TF minus T0, that's like delta T. And delta D is final distance minus original distance, starting distance. And I know that speed is distance over time, which then I could write like this, T final minus T0. And since I know, then I look, do I know any of these? And I would, in my head, I would go, well, I know V, I know final distance, I know initial distance, I know initial time, and I'm asked to find final time. I have all the pieces in my equations, and I can solve for this. So yes, this is the equation I should use. Then I go put in the numbers and solve.
Okay.
And this was it was a very good practice. And now I
It's a
don't.
good approach.
Yeah. After doing it so many times, it became how I think. And now I don't always write down all the things, but in my head, I make sure that I'm clear before I write other things. So I'll just move that over there. And maybe we can make it a bit smaller. Whoop. Not that kind of smaller. You can get smaller. So this was just meant as an aside. But now we're going to go back to our original question. Put this over here. Okay, so we are interested in the derivative of x cubed minus x over x squared plus 3. And we think, so when you look at it, you say, ooh, it's not as simple as using just like the power rule or
Yeah.
something. So you're working on it.
Yeah, I was actually working on
Okay.
it.
So the first question is, it looks like a quotient, obviously. And so we have an f and a g. So the f part is what?
X
So I would
cubed
write x cubed
minus x.
minus x, and the g part is
X squared plus 3.
x squared plus 3.
Yep.
And then we have our equation up here. So we need f prime and g prime, and then we should be good. So what would be f prime?
F prime is 3x squared minus 1.
And g prime is
2x.
what about the plus 3?
No, it's more like a coaster.
Yeah.
Yeah, so I think it's going to be 0. It's plus 0.
Very good.
Yeah.
Just checking. All right. So now we apply our f prime times g. So f prime times g is 3x squared minus 1. And g is x squared plus 3. And then f times g prime is x cubed, minus x, right? Times 2x.
Yeah.
So now we can expand these. So what is the expansion of these? And I guess we have g squared. We could also do g squared, which is x squared plus 3 times x squared plus 3.
So this is what I came up with.
As the final
No,
answer
no. Like here,
for the f prime times
f prime
g.
times g.
So 3x squared times x squared is 3x to the fourth.
To the fourth.
Mm-hmm.
Oh,
X squared times x squared is
yeah.
x to the fourth.
That's way I was.
Okay, and then 3x squared times 3, that's 9x squared. Then we have minus 1 times x squared, so that's minus x squared. Minus 1 times 3 is minus 3.
Yeah.
Let me just move these over a little bit so we have more space for the other one here. And this will be, well, this one is easier. X cubed times 2x is 2x to the fourth. Minus x times 2x is minus 2x squared.
So x squared plus 3 multiplied by x squared plus 3. So this becomes, this times this becomes x fourth, and then plus 3x squared, and plus 3x squared,
So then
and plus 9. So this becomes x4, and this becomes
minus g prime times f
6x squared plus
3x4 plus 9x squared minus x squared minus 3. And 2x to the 4 minus 2x squared. So we have 3x4 minus 2x4, that leaves 1x to the fourth. We have 9x squared minus minus, that's a plus 2x squared, so we have 11 x squared. Or we have a minus an x squared, we could have simplified that. So, let me go
Really?
Hmm?
We're here.
We are where? 9x squared, yeah, so 9x squared minus x squared is then 8x squared, right?
Yes.
So 8, and then minus minus, is this 2x?
Yeah.
Are you sure?
Oh, it's 2x squared. Okay.
So if we have a 9 minus 1 is 8, minus
this
2.
becomes positive, so 8 plus 2.
Mhm.
That's 10.
10. So we have plus 10x squared.
Plus 10x squared.
And anything else? Then we just have them
And minus 3.
minus 3.
X fourth plus 6 is 2. Plus 9.
And then the gx squared, let me move it down here. And so that was x squared plus 3 squared is x to the fourth plus 6x squared plus 9.
Yep.
So now we put it all together and we say f over g prime is f prime g minus g prime f over g squared, which is x to the fourth plus 10x squared minus 3. My 4s don't look like 4s. Over x to the fourth plus 6x squared plus 9. Now, and this is the answer. Now it's possible that this could be factored, depends, maybe not, that this could be factored in a way that we could simplify, which would just make it look nicer, but it would still be the same answer. And we just chose these functions, so I don't know. Does this, the denominator obviously factors into x squared plus 3, because that's where it came from. So then one could ask, is there any way that the upper part can factor into x squared plus 3? And I don't think so. You need two terms that sum to 10, two numbers that sum to 10, and whose product is minus 3. And you can't get that because minus 3 is only 3 and 1, with one of them being negative. And 3 and 1 added together or subtracted does not make 10.
What about using the quadratic equation? Doesn't it?
Yeah, you could, but that's if you want to solve for x.
No.
I was just thinking, how can we simplify this expression?
No.
But no, there's no simplifying it. So this is the answer. And now we might say, well, what does this equation look like? I mean, that looks pretty big and complicated. So let us. Is there a way to? Am I allowed to do that here? Yeah. And I hope that's still going. We are going to use Grapher. So x to the fourth. So we have our functions x cubed minus x. So y equals x cubed minus x divided by x squared plus 3. Right? So that's the function. That's what it looks like. Okay? And then I can do another one. And we are interested in, I don't need 2 y's, but I do need d by dx of this thing. And, sorry, no, I just need that part. So now this line is the derivative of the first one. This thing here. The computer's doing the derivative up there. I don't know if I can make it bigger. But we did it ourselves, so we could check, is x to the fourth and x to the fourth. I told you to be done. Come on. Where are you? X to the fourth
Plus 10x squared
plus 10 squared
minus 3.
minus 3. And then all of this, x to the fourth
Plus 6
6x
squared
squared
plus 9.
plus 9. And what should happen is that this equation should be exactly the same as this derivative equation,
Okay.
right?
Yeah.
So this is the original function, the just f divided by g. Then the derivative of it, the computer is doing. I told the computer to do this, and this is what we've added. So now if I hide both of the derivatives. This is the one that we have calculated.
Okay.
Right?
Yeah.
Looks good. And now if I hide it and I show the one the computer does, they look pretty close. If I show both, then I would expect one of them, if they were different, then I should see 2 lines.
2 lines.
But I don't, I see 1 line. So this confirms that we have, in fact, correctly differentiated just quotient of 2 functions.
No.
How exciting! All right,
Yeah.
so you know how to use the quotient rule now.
Yeah.
It just takes some careful working through, making sure we track our powers and the pluses and minuses, and that's usually what goes wrong. When we get the wrong answer, it's not because we didn't understand the rule, it's because we made a mistake somewhere in the algebra, keeping track of things. Good. So that's the quotient rule. Now, the chain rule, how could we use the chain rule? Okay. Let's try it like this. Let's try it with an example, actually. What I hope will be a simple example. So the chain rule is defined. You have a function f of x. Sorry, go back. You have a function f of x and a function g of x. Now, before we even get into differentiating, are you convinced that it is allowed to then write this?
Yeah.
But if I have a function f of x and I have a function g of x, I am allowed to take f of g of x, the composition of functions. I could also do g of f of x, which might be the same thing or something else, we don't know. But these are things we can do, right? Okay. If you know that, then we're going to be good. So the chain rule says, all right, I know how to differentiate f of x, assuming I know how to, let me put this back on the screen for our friends to see what we're doing. So we're moving on to the chain rule. So given a function f of x, a function f of x, a function g of x, I can make the composition f of g of x or g of f of x, and these may or may not be the same thing. That's not an automatic. So now we'll do it with an example first, and then we'll so the question is, if I have this, what is the derivative of that? Or what is the derivative of this? That's essentially what we want to know. If I give you two functions and I say now I compose the functions, and I ask what is the derivative of its composed function, you go, how do I do that? And so sometimes you actually do f of g of x and you come up with a longer expression, and then you can take the derivative of that. It becomes a single function. But maybe it's, in some cases, it won't be easy to do that. And also, for theoretical cases, it may be very useful to be able to do this. And so one use, in a theoretical sense, was to prove the quotient rule, we used the chain rule. Now you're going to ask me, how do we prove the chain rule? And I will say, I don't remember. I would have to look that up in the textbook.
Fine.
But if you're okay with looking that up on your own, and we can discuss it another time. If you follow the proof and you agree with it, then fine.
All right. If I have questions, I'll come back.
Yeah. So I know when I was a student, I was in a program where it was more important that we learn the proofs and really understand them and kind of be able to do them, because that was the career that I was pursuing. But for the kinds of careers you guys are pursuing, you don't need to be able to prove these results, but you need to be convinced that they work. And so I don't want to focus so much on proofs, but more on using the results. So the chain rule deals with this question, and we'll use a simple example, and you might say, oh, this is kind of obvious, why even bother? So let's say f of x was x cubed, and g of x is x squared. Right? So what is the composition f of g of x? Well, f of g of
Can we
x,
try using something that I saw?
Sure.
I think it was, what was it? It was x cubed e, like that, something like that.
X cubed e to the 2x. You want to use an exponential function? We haven't seen exponential functions yet. Do you know how to do the derivative of an exponential function? So you want to do x cubed e to the 2x. Do you know what e to the 2x is?
No, I just
Alright.
saw the question.
So how about, it's a good one, but how about we keep it and come back to it as a, so the question is, what is the derivative of this thing? So this will be partly I want to put it aside because we don't yet know how to do an exponential derivative, the derivative of an exponential. We will learn, but we don't know it yet. So for the purpose of understanding the chain rule, let's use simpler functions that we know, and then we'll come back to that. So, how am I doing on time? Oh, it's just 9 o'clock. Great. So f of g of x in this case would be
G of x. sorry. We're taking x squared into x cubed.
So what would be that? So x squared into x cubed.
So it'll be x squared cubed. Like that?
So we have f of, now g of x is x squared, so we have f of x squared, and f is cubing the thing, so we have x squared cubed. Perfect. Now this happens to be easy to do. X squared cubed is what? Can we simplify that?
Can we say that it's right? We're having 3 of them. So x squared multiplied by x squared multiplied by x squared, right? So we have x squared multiplied by x. Yeah, x squared. So we just add up the
Powers, the exponents?
6, and this would be x to the power 6.
Yeah, x to the power 6. So as you correctly noted, let me put it in gray. This is x squared times x squared times x squared. And so you can add 2 plus 2 plus 2. And you can also remember, if you have a power and then the whole thing raised to another power, you multiply the powers. You're going to have 3 instances of x squared. So it's 3 times 2 is 6. Very good. So we'll remember this for when we come back. Now, the chain rule says, the actual definition of it, that d of f of g with respect to x is df dg times dg dx. Which might look a bit, what does it mean? You know, all this time we've said a derivative is d by dx, the variable that is in the function. So suddenly we're saying, oh, but we're doing now the derivative of a function with respect to a function? Well, not exactly. For the purposes of when we are looking at this term, we consider g, right? When you write f of g, where did I write f of g here? We consider g, actually not in this case here, let me undo that one. Yeah, go away. But in this case here, g is considered a constant. But over here, it's considered variable. I say that and I realize that probably sounds weird. How can it be a constant and a variable at the same time? But Dr. Squires, that doesn't make sense. And you're kind of right. So it's not that it's that we are considering it as, let me move this over here and say, okay. So what do we mean? Well, we know f of x is x cubed. So if I were to write, instead of writing f of x, so we said f of x is x cubed. But x is just the name of a thing. It's the input to the function, right? If I were to write f of g is g cubed, I would still be saying the same thing. The function still does the same thing. Or I could have f of y is y cubed, or f of name is name cubed, right? Whatever is in there is simply a symbol for the thing that goes in, right? The function doesn't care what you call the input. What the function is a thing that cubes whatever you put into it. That's what f is. It doesn't actually care what we call the thing you put in. So when we write df dg, we're saying d by dg of f of g. which looks just like doing d by dx of f of x if we had defined f of x. So in this case, we say, okay, well, f of g is just g cubed. That's fine, right?
Yep.
And we're multiplying this by d of g of x dx. And so when I said x is like, it's not that x is a constant, that was probably the wrong thing to say. But x is the variable, the input variable to f. So it's not a function in this case, it's a function when it takes x. But now for the purpose, in relation to f, g is just whatever you're putting into f. So you put in an x, you got a g, now you have the g. It's a thing now. The function has done its job, right? And so, right, we had g of x is x squared. So if I had a 3, I squared it, I got 9. So g is now 9, for example. So now, what goes into f? 9 goes into f. Or, I mean, these are variables, so we can take any value. But so now we should be able to do this, right? F of g, d by dg of f of g would be what? So this would be what?
It's 6 squared, right? Which we're having
So
our g was x squared, right?
g was x squared, f was x cubed.
Yeah.
So f of g is the same as like f of x. It's just the x cubed.
yeah, so x cubed of the.
So what is the derivative of x cubed in this sense? Or in this case, let's write more. This is now g cubed, d by dg. Right? That's what f of g means.
Yeah. And our g is x squared.
I don't replace g.
We don't.
Nope. Now we just say g cubed, the derivative with respect to g. I don't want an x. I'm not differentiating with respect to x. I'm differentiating with respect to g.
So it would be 3g squared.
Correct. So this will become 3g squared times, and then here I have dg of it. Now g of x is what?
G of x now is x squared.
Is x squared. So this is x squared by dx. And what is that?
Plus 2x.
That's 2x. Okay. Now g is a function of x. Now I want this all as a function of x. So now I substitute for g. So what is g?
X squared.
Is x squared. So now I put my x squared times 2x, and that's equal to.
So we have 3 multiplied by x to the power 4.
Times 2x, and that is.
And that's going to be 6x to the power 5.
Let's check if this is correct. So remember, at the start we said, because these are very simple functions, we can do the composition, and we got, if I compose the two, I get x to the 6th. So I could also say, what is the derivative of x to the 6th?
That's 6x to the power 5.
And
Okay, I see what you did there.
now, of course, we did it the long way, right? If you actually had these, you would just say, well, this is easy, it's x to the 6th, derivative of x to the 6th is 6x to the 5th, we're done. Why would I go through the chain rule? The answer is, you wouldn't. I only did this as an example, right? To show how the chain rule works. That, let me see if I can motivate the chain rule. So, in the world of business, since you're studying business accounting, right? So in the world of business, you might have a function. What is a function that is a something is another function? I know. Let's say we have a tax function, and you have a sales function or revenue function. Let me call it revenue function. Actually, income, because you're taxed on your income. If you're a firm, you're taxed on your income. So let's say your income, I don't remember what do we use for income? Are you getting distracted by your phone?
I was just checking if Mona answered my text because she wasn't. I thought she's gonna come.
Also, our dear Clement was not. He said he would join, but maybe his internet is. Sorry, I need to. Well, for income, we'll just use I. That'll make sense. So income might be a function. What does income depend on? Let's say it depends on sales. We'll call S sales. And, or actually, it's a function of price. So let's say my income is, the higher the price, well, income is revenue minus costs, right? And so you can decide what is a simple function for revenue as a function of price, or maybe quantity. You know what? Let's do quantity. Sorry, I know I'm going back and forth, but I'm trying to think of something that will be simple enough for us to think about. Quantity Q. So the more, Q is the thing I sell. So what is my revenue as I sell more things? Well, maybe it's 1,000 of quantity. The more I sell, the more revenue I get. And my cost is, let's say 500 Q square root of Q. I say square root of Q because the more I make, the lower my marginal costs. Do you see how square root of Q means that costs will grow more slowly than revenue?
Yeah.
Okay. So let's say this is my income function as a function of quantity sold. Now the tax function, the government says, right? They say, we're going to tax your income. We don't care what your quantity is, that's your business, but we tax your income. So the tax function is a function of income, and the tax function might be, what do you think the tax function might be? How does the government decide how much tax you pay given your income? So let's say your income is 1 million kwacha. Not very much for the year, right? What should be the tax? Is it a percentage?
Let's say 30% of it.
And if your income is much higher, like 1 billion kwacha, is it the same percentage?
No.
No? Okay. So there's a rate, there's a tax rate. A rate times an income. But the rate will be a function of income. So we'll say the rate is like 0.3 to the I squared times I. Wait, no, that's not what I want. That's going to be too complicated. We'll just keep it at 0.3i. It's a simple function. So 30% of, so let me take off the depends on I. To be more realistic, if you have a progressive tax, right, that the first little bit of money you make, no tax. When you make a bit more, the tax rate is low, and then it gets higher the more money you make.
So
we could write an equation that does that, but let's keep it simpler. So we'll just say it's a straight, constant percentage of your income. This might be too simple in a way, but So now you say, well, I would like to know, how does the amount of tax I have to pay depend on the quantity? We have a business decision to make. Should we produce and sell an extra 10 quantity of whatever we make? Let's say we make equipment of some kind or whatever it is, yeah? If we make this 10 more, how much tax will we have to pay? And how does the tax we have to pay change as we change our quantity? Okay, that's the question. Now that you can imagine is a question might actually happen in everyday life. So you would say, well, your tax is a function of income, and income is a function of quantity, right? And so what you want to know is, how does tax change with quantity? We're interested in this. How fast does my tax rate increase, right? Is it worth trying to produce and sell more if I continue to make and sell more? Because remember, derivative is a rate of change. Is the tax the amount of tax, right? The tax function is the amount of money I have to pay. Is that amount going to grow more quickly or more slowly as I add more quantity or decrease quantity? So you would like to know this, right? Or your client would like to know this. And you're a very good accountant and you say, my friend, I will let you know. Let me go look up the same rule. So, how would you approach this? Knowing what you know now.
That just looks so complicated.
Well,
So it's
so remember, this is where it's useful to, let's write down what we know. So what are all the things you know? And we can rewrite the same things that are on the screen, but start by,
okay,
actually,
we know the function of
so you're so you want to be clear. What am I being asked?
Okay, so I've
What
been
do I
given
know?
the function of tax. Okay, which is rate multiplied by I, right? And then have income function, which is I of G. That's Q, right?
Q.
Whoa. Okay.
And what are you asked to find?
Okay, so trying to find T, which is the function of tax with respect to the income function. Okay.
Actually, that's not what you're asked. I just realized as you wrote it, I said, actually, we could start with this though. Okay? So there's two different things. One question is, how much tax do I have, right? T is the total amount I have to pay. You tell me what the income is, and then you say, well, tell me the quantity, I'll know the income, then I know the income, then I can calculate the tax. And that is the amount that I have to pay to the government.
Okay.
Right? That's what you've written down. That's the total amount. The next question, and we should do that. That should be step one. What is that function? The next question would be, I'm interested in knowing, is it worth it for me to change my quantity? How will the amount of tax change as I change the quantity?
You kind of roast.
Okay. So, let me write. So t, as what you've written, t of I of q, right, is the total tax owed for a given quantity q. Correct? All right. And so if I were to plot a graph, right, what I know t as a function of I, and it's 0.3i. So is this a linear function? Is this a linear function?
Yeah.
Yeah. What is the slope?
The slope.
If it's a linear function, it has a slope, right? What is the slope?
0.3.
0.3. Very good. So, is that a steep slope or a shallow slope? Is it bigger than 1 or less than 1?
It's less than 1.
Okay. And 1 is the 45-degree line, right?
Yeah.
That's a slope of 1. So 0.3 would be something like that. Okay. So get rid of that. So this is t equals 0.3i. Now we have another graph over here, and it's a little bit crooked. Let's try and draw it straighter. This is I as a function of q. And this function was 1000q minus 500 square root of q. So it will probably be something like, I'm totally guessing, but I think it will look something like that. Ish. Right? The more quantity I make, the higher my income.
Yeah.
Okay? So this is I equals 1000q minus 500. And I'm going to put q to the 0.5. Instead of writing square roots, we'll put to the power of 0.5. You know those are equivalent? You didn't know that? That square root of x is x to the 0.5. We can prove it very easily. So let's take a moment. This is important. So if I take square root of x times square root of x, what do I get?
Square root of x squared.
Which is what? How does that simplify?
It just looks like x.
Because the square root of x is the thing, the number which, if I multiply it by itself, gives me back x. That's the definition of the square root, right? It's the thing which, if I square it, I get back the number. So the square root of 4 is 2, because 2 times 2 is 4. The square root of 9 is 3, because 3 squared is 9. Right?
Yeah.
That's a square root. Now, we know the rules of powers, right? If I have x to the a times x to the b, you know that this is x to the a plus b. So, if I have this square root of x is some number, we don't know yet, we'll call it a, and if I multiply it by itself, then I get, it's also a, and this should be equal to x, or x to the 1. In other words, 1 should equal a plus a, right? Which is 2a, and therefore a is equal to 1/2.
Oh, that's why we're coming up with 0.5.
So ax to the 1/2 equals square root of x. Same thing, just written two different ways. And of course, 1/2 is 0.5. So I could also write this as x to the 0.5. All three of these are the same thing.
Okay.
And then similarly, you can, by the same exact process, you could show that the nth root of x is just x to the 1 over n. So square root, we don't write the 2 usually. We just all know that if I just draw this, that means the squared root. But if I mean anything else, the cubed root, so I can have the cubed root of x, which is, what is the number that multiplied by itself 3 times? So cubing it gives me back x. If I put here 30, then what is the number which multiplied by itself 30 times gives me x? And if it's multiplied by itself 30 times, then if you go through the same process, you will find that this is the same as the number x to the 1 over 30. Or whatever. So this is the general formula for fractional powers. Okay, so that was just a aside. Let's give it a name. Let's remember that this is fractional powers. And we'll put it in one big box. So that's why I wrote q to the 0.5 over on our chart here, right? This 0.5, that was the square root that we had over here. So we have these two functions, and essentially I want to know, right? So if I change q, if I had a q that was this quantity, call that q1, okay, well I could, I would have a I1, there would be some number.
Yeah.
And then I could take that I1 and go, okay, here's I1, so then I know tax for I1, right? So in a way, I knew Q1 and I ended up getting T1. That's the composition of functions. And I could change Q1 and say, what if Q1 becomes Q2? Then it'll be something bigger. I will get an I2. I2 might be over here. And so I'll get another tax 2. And so on. But now I say, so from here to here, there was a change. Right? Let me use a different color actually. Let's maybe try green. So if I go from Q1 to Q2, I know how much the quantity changed. There's a delta Q. And given that delta Q, I changed by delta I. So you could find what is the slope. And I could find what is the instantaneous rate of change. If I change Q a little bit around Q1, how much do I expect my income to change? Do you know marginal cost, the idea of marginal cost, or marginal revenue, marginal anything in business and accounting?
I think I've written it in macroeconomics.
Mm-hmm.
Yeah, but
Not so clear on it yet.
yeah, I don't actually remember.
Okay. The idea of a marginal something is, given I already have a number of sales, or an amount of supply, or an amount of tax, or an amount of something, by how much, and it's a function, so, or consumption as a function of price, supply as a function of price, demand as a function of price, tax as a function of production, something as a function of something. The marginal is if I change the independent variable, right? So in this case,
if I changed Q by 1 unit or by a tiny amount, depends on if it's a continuous variable or a discrete thing. Like cars, you don't make fractions of a car. You either make a car or you don't make a car.
Yeah.
So you could say, well, to add 1 more unit of car, how much would that change my either costs per quantity or income per whatever your function you're interested in? How much does it change if I add 1? Or if it's a continuous thing, like an amount of water or electricity. Right? Electricity is continuous. I could make this much or decimal, or I can make all different amounts of power. So I say if I add a little bit more power, how much, by what fraction does that change the dependent variable? So in this case, my income. If I make a little bit more power, does my income go up by more or less as I do that? And in general, so that's another way of saying what is the instantaneous rate of change at the point Q1. And the idea of the marginal function is that you can now tell me for any quantity, I can tell you if you have a particular quantity, your marginal change will be this. In other words, it's the derivative. The marginal, so it depends on what the thing is you're studying, cost function, the marginal tax, the marginal production, the marginal revenue, the marginal sales, whatever the function is the derivative of that function. And the idea is on the margin, right? So if I already have Q2 and I add 1 more, what does adding that 1 more give me? Adding 1 more here will give me a different increase than adding 1 more here, for example, right? Down here, adding a little bit more will give me, I don't know, +3. But adding a little bit here gives me only 0.5. And adding a little bit here gives me 10, right? How much it changes depends on where I am in Q. Adding a little bit more doesn't always add the same thing. Does that make sense?
Come again.
Is this making sense as I'm explaining it, or no?
It's just too much about the marginal.
Okay, we'll come back to that. The textbook probably does a better job of explaining it, but we can also review it. I wasn't planning to explain what is marginal things, but the key thing, the takeaway, essentially, is that marginal functions is sometimes abbreviated FN, so I'll just write marginal functions are derivatives.
Okay.
So even if we're not quite sure what does a marginal function mean, at least we can remember it is a derivative. And that's, I was trying to motivate what we're doing if you knew what a marginal function is, but if you don't know what it is yet, then it's not a very good motivation. All right. So back to our original, let's just put us back, right? We are a firm. We produce something, quantity Q, which provides us with an income, and then we're taxed on that income. And so, of course, every year you have to calculate how much tax do we owe. Well, this year we produced 33. Okay, 33, what is the income, and therefore how much tax? And next year we produce 37. And so how much tax do we owe? We can compute. That would be doing this here. Right?
Yeah.
And then, we're trying to increase, and we really, we invest a lot in our in our facilities, and so next year we produce 56. Okay, how much tax do we owe on 56? And so on. And every time we increase Q, of course we increase our income, but that also means we increase our tax. And now your boss says, well, I would like to know, right now, when I go from 33 to 37, I added 4 quantity, my tax increased by something. And now we're making 56. If I were to go to 60, which is also plus 4, right? 33 to 37, that was plus 4.
Yeah.
56 to 60 would be plus 4. Will the difference in tax be the same for adding plus 4? Or will that difference in tax be different? What will the difference in tax be? That's what your boss wants to know. If I add another 4, now that I'm making 56, is my tax owed going to be the same as the extra 4 that I had 2 years ago? Or will it be something else? That's what he's asking. So what will that difference be? Not what will the total amount be, what will the difference be? When someone asks you, what will the difference be? Or how will this change depending on how something else changes? Then your mind should immediately go, aha, I need a derivative. What I'm doing is, now, in your mind, you're doing the operation of differentiation. Sometimes you actually have the functions written down. Sometimes just the idea of it is what you need. But in this case, we're going to do it with actual numbers and variables. So now what he's asking is not simply how much total tax do I need to pay, but how does the total amount of tax I have to pay depend on, or how does it change as the quantity changes? That's what we're interested in. So we have a composition of functions. Okay, let's skip past our fractional powers. Or we have these graphs here. So we understand how quantity leads to an amount of tax. And when you look at the graph of income versus quantity, it's kind of obvious. Well, if we are in this area here, the income grows slowly with quantity. Right? Yeah. Slower than up here. Once I'm making more quantity, adding a little bit more gives me much more income. So I would like to be over here for quantity, if I was a business, right? But then he says, but how will tax change as a function of, I'm sorry, I'll talk right now. How will my tax change as quantity changes? Right, when I'm down here, does my tax change? My income changes slowly. Does my tax also change slowly? And if my quantity is here and income goes up much faster, will my tax also go up faster? Or what will happen, right? That's what you want to know. Yeah. So we use the chain rule. And let's see. So let's just write our things down here again to remind ourselves. So we have the tax rate, tax function is 0.3i. The income function is 1000 q minus 500 q to the 0.5, and now we know what that means. And what we are asked is, what is t of q prime? That's essentially what we're asked. But now you look at it and you say, well, t is not a function of q. T is a function of I. Yeah. I is a function of q. So t of q is actually t of I of q. That's how I get t of q. So when you ask me, what is dt dq? Okay, well, I don't have t of q. That's not given, but I do know t of I. And t of I is a function of q. So indirectly, tax is a function of quantity.
Yeah.
Okay. And you want to know how tax changes as a function of quantity. Well, this might be complicated, except I know the chain rule. And the chain rule says that I can first figure out how does tax change with income, and then how does income change with quantity. And this, now we can do this. I think. How are we feeling so far? Do you follow the
Yeah.
logic?
Yeah.
So what is dTdi?
DTDI. So it would be.
Sorry, I know the thing under here
Yeah,
makes it
yeah.
hard. Get out of your way, you can come and go. Just let her know.
Oops, I think I did something here.
Oh. Yeah, if you hold down long, it brings up
No.
this magnified thing.
DTDI is I